Finding the Mohr integral using the Vereshchagin's method. This is article number 3.h of the book Mechanical Systems Calculations of the Marine Facilities. To simplify the use of the product of diagrams of the bending moments to find the displacements using the Mohr integral, sometimes we had to use the approaches which we can indicate three widely used approaches: Vereshchagin rule, which we will consider on this definite one article. As well, we have a trapezoid rule. Trapezoid, if we can consider the bending moments and under the action of the unit effort in the direction in which we have to find the displacement of the mechanical system. And as well, we have the Simpson method. Simpson, we will probably look at Simpson method a little bit after. So now we are talking about the Vereshchagin rule. Vereshchagin rule of the product of diagrams in the integrand when finding Mohr integral. Mohr integral consists of the product of diagrams in the numerator in the integrand. And for the increment of the variable is the value of the coordinate of axis coincided with the element of the mechanical system, which one we consider. Sometimes we can deduct the in the fraction in the integrand, we deduct the denominator. Denominator we have to indicate generally for the Mohr integral. We have to consider as well the to this integrand the denominator. Denominator here is the under the product of the diagrams we have in the denominator the product of the elasticity modulus and the index of the moment of inertia of the area of the cross section of the element of the mechanical system. So, but it is out of our interest because we will talk about the product of the diagram. So we can not consider this consider it sure for the theoretical conclusions about Vereshchagin's rule to find the product of diagrams in the integrand of the integral of Mohr. We can sometimes not consider the denominator of the integrand by the rigidity indexes of the element of mechanical system. So to use Vereshchagin rule to simplify the product of diagrams, yeah, exactly. If we have the mathematical equations for dependencies of the each of diagram of the bending moment under the influence of bending moment of the mechanical system and the influence of the external load, and if we have the mathematical equation for the bending moment of the mechanical system elements and the influence of the unit force in the direction of the displacement subject to find by the Mohr integral. In this case, we will use the Mohr integral to determine the displacements of the point of the mechanical system in the required direction, which one we have to find the displacement. We can do as finding the integral directly, but sometimes we do not have the mathematical equation of the diagrams, and we have only the ordinates of diagrams, that is magnitudes of the bending moments at the ends of the diagram. For example, here for the trapezoid diagram of the bending moment of the assumed element of the mechanical system and the action of the unit force. Unit effort, maybe unit not only force, but maybe unit moment, etc. in the required direction of determination of the displacement. Yes, and the assumptions for use of the Vereshchagin rule is that we assume the diagrams of the bending moment adjection of the external load on the element of the mechanical system and the bending moment diagram action on the on the mechanical system of unit load in the required direction of finding of the displacement. And we assume that we have these two diagrams for each element of mechanical system as trapezoids. Trapezoids may be a linear trapezoid like here for the unit force, or maybe non-linear. But assumption for Vereshchagin rule is that at least one of the trapezoid have to be linear. One have to be linear. It could be usually the diagram of the bending moment injection of the unit effort. It can be linear inclined distribution of the bending moment along the element of the mechanical system, or it can be even distribution. It depends on what is geometry of the mechanical system at which we have the load of unit force. It can be the effort like a force, or it can be effort of the moment. If we have the moment, so for the case of to find the angle of bending of definite point of assigned definite point of the mechanical system, and we have to consider this point adjection of the unit moment. In this case, usually in this case, the diagram of the bending moment adjection of the unit force, the bending moment diagram for the element of the mechanical system could be even distribution. And if we consider the bending moment adjection of the unit force, it can be linear distribution inclined of the diagram of the bending moment of unit force, in this case, not effort, but force. And the even distribution in definite case. It depends on the dependence on the diagram in geometry of the mechanical system. So what is the rule of Vereshchagin to determine the indicated here Mohr integral with not only the denominator here, with not the characteristics of the rigidity of the mechanical system, because we consider only the product of the diagrams in the Vereshchagin rule, and we just deduct and remove considering the denominator of the rigidity characteristics of the element of mechanical system. So the integral of the product of the bending moment, for example, the first one can be the bending moment of adjection of the external load, I mean M bending moment, and the second is in the product the bending moment adjection of the unit effort on the mechanical system element, but it can be another one sequence. It's not so much important. We just have to obey the rule that if we, for any one element of the mechanical system, use definite sequence of the product of the moments or diagrams, first one to the second with the Vereshchagin rule, we have to keep the same sequence of the product for any other elements of the mechanical system. Not for the one we can do the one sequence, for another one sequence. We have to obey the same sequence for all. So let's consider the abstract element of mechanical system with a bending moment diagram of the external load. We can indicate here the pure linear diagram just of the arbitrary shape. Smooth surface, but anyway, curvilinear diagram. We have two magnitudes at the ends of the diagram, and we can find the area of this diagram. Sometimes we have the usual formulas to determine the area of parabolic diagram. Parabolic are non-linear diagram. It's very easy to find if you have a linear diagram, the area of the diagram. It can be the for trapezoid. We have the formula as a half total of the ordinata of the at the end of the diagram trapezoid multiplied by the h of the trapezoid. For the curl, it will be difficult. Some we have to find the area using the formulas for the parabolic, or maybe for the cubic parabolic shape of the one of sides of the curvilinear trapezoid. In this case, we assume that we have the area of the omega Greek letter, omega lowercase, the area of this curvilinear trapezoid diagram. We have the location of the center of each area, center of area of this curvilinear diagram. So in the projection connection with other one diagram for the same element of the mechanical system, for the diagram of bending moment on the same element mechanical system at the action of the unit effort, we have to find the magnitude or the diagram ordinata in the correspondence in the projection connection with the location of the center of area of this curvilinear diagram of the same element of mechanical system experienced the external load with not unit force. So how to explain that? Why does this product correspond to the product of the area of the curvilinear diagram of the bending moment and action of the external force by the ordinata corresponding to the center of the area of the first one diagram, ordinata of the second one diagram? Why does this corresponds to the integral of this two diagram product? That's why we have to consider that if in the general approach we have the inclined side of this trapezoid diagram, could be the diagram of the bending moments and action of the unit forces, we can define that if we assign the reference point of the system of the coordinate in the flat state for the plane, we assign with the point of the intersection of this line of the one of sides, inclined sides of the diagram of the bending moments and action of unit forces. When it intersects the axis, horizontal axis, we coincide with the same one place, the reference point of the coordinate system. So if yes, the magnitude of the bending moment and influence of the unit force in the independence on the abscissa counted starting from the reference point 0. Abscissa is for the bending moment for this definite one assigned diagram of bending moment and action of unit force, the bending moment will correspond to abscissa and equal the product of abscissa of definite one point by the tangent the angle of the inclination alpha. So considering the introduced notation, the product of diagrams in the Mohr's integral takes the form as the product of two diagrams, and this equal to the increment of this area equal to the product of the tangent alpha assumed. Perhaps we know the angle alpha of the inclination of this side of the trapezoid of the second one diagram. But we can deduct it out of the integrand, and we can remain at the integrand only the increment of the area corresponding to the definite one abscissa magnitude. So the area increment is d omega area, and the product by the sign, product by the abscissa of the considered one point along the element of the mechanical system. So this is increment of the dx increment of this of the abscissa. This is the increment of the area corresponding to this increment of the abscissa. Increment of the area of the diagram of bending moment on the stretched fibers of the elemental mechanical system experiencing the external load. So this production increment of the area finally give us the area of this one, the diagram of the curvilinear shape of the bending moment and of the element and action of the external force. And the integrand remains here when we deduct tangent alpha out of the integrand. Remains integrand area nonlinear diagram of the bending moment shows this is a static moment of the diagram of the bending moment of curvilinear related to the axis y, ordinate axis y, due to this integral equivalent to the. So this integral remained here equivalent to the product of the total area of the diagram of the bending moment by the abscissa of its location of center of the area due to the on other hand the static moment of the area relative to an axis is equal to integral of abscissa the distance between the definite axis assigned to the increment of the area, considered area, by the arm. Arm is abscissa itself, and this is on one hand static moment of this diagram relative to the axis, static moment of area of the moment diagram, and on the other hand, this static moment equal to this area of the diagram, not the moment but the area, multiplied by the abscissa of the center of the area, of this one area. So after mathematic transform, we can find that the product, we say product of the diagrams actually is the integral of the product of two diagram bending moment of the bending moments of element mechanical system at the action of the external load by the bending moment of the same element at the action of the unit forces, usually linear, and equal on the other hand as the product of tangent alpha angle of the inclination of the linear bending moment diagram by the line by the extent from the axis y of the center of the area of the curvilinear diagram first in the integrand, and by the area of this one diagram first in the integrand as well. And finally, this corresponds as the tangential product of tangent alpha by the abscissa of the point of area of the first one diagram and the integrand. This is that ordinata tangent alpha by the product by xc corresponds to bending moment magnitude in the point when the diagram of the bending moment and action of the external force has the center, geometric center, the same one. That is because tangent alpha product by the abscissa xc of the center of the area of the first one diagram, the integrand is equal on the other hand to the moment of the second one diagram for the same extent from the ordinate along axis x perpendicular to the axis ordinata y. Okay, so let's use this rule of Vereshchagin to determine the product of the diagram and the displacements of the points of the mechanical system. So it is assigned the mechanical system about the same as it used to be in the article 3.7, but this is in 3.8. In the article 3.7, we decided the Mohr integral, and we determined the displacement of the horizontal displacement of the point C and direction of the transverse force here in the direction of the transverse direction of the point C. And now we have to determine three displacement of the point C. I mean the horizontal displacement, vertical one, and the bending of the angle, the bending in the point C, and direction of the load. We have load on this mechanical system, statically definable exactly. The system loaded by the distributed force equal to kilonewton per meter by the bending moment rotating counterclockwise equal 7 kilonewton by meter, and the transverse force leftward 9 kilonewton by meter. So the question is to find the displacement of the point C left along the horizontal line, in vertical displacement, and the bending displacement of the point C. First of all, we have to determine the diagrams of the external load of the bending moment and the action of the external load. And besides all that, we have to find the characteristic magnitudes of this diagram, the ordinates of the diagram. Due to for use of the Mohr integral and the Vereshchagin rule, we don't need to have so much mathematical equation of the dependence of the bending moment along the definite variable coincided with each with the definite one of the element of mechanical system, but we have to have the points of the magnitudes of the bending moment using the digital calculations with not the direct integration. We have to use we have to use the digital approach to find Mohr integral by the Vereshchagin rule. So, on the action on the point C and the action of the moment applied 7 rotated counterclockwise, we have the first the ordinate of bending moment diagram 7. In the point, this is with not distributed load leg of the CB is do not experience the load distributed along this CB element of the mechanical system. So we need to have the bending moment diagram have to be linear, and we need to have two magnitudes at the ends of the diagram to have the L shape of the linear diagram of the bending moment for this definite one element of the mechanical system CB. So as the applied concentrated force rotate clockwise around the point B, and applied bending moment rotate counterclockwise, so they have another signs, and in the point B we have -11. -11 mean that we have the bending moment here in the point B action caused by the force concentrated force 9 kilonewton by the arm 2 meters. So 9 kilonewton 2 meters and 18 kilonewton by meter the bending moment on behalf of force F. And on behalf of the assigned moment, we have another sign, and 18 minus 7 is 11. So we have 11 kilonewton by meter moment here of the another sign, then in the point B of the another sign, but then in the point C. And we have 2 points, and we have a straight line, and this is the diagram of the bending moments on the element CB of the mechanical system. For the leg, AB, we can find that the bending on behalf of action of distributed load and on behalf of the moment we have in the point B, this rigid corner, the moment is transmitted through this corner, and this is 11, like here we have 11, and this is 11, and the predominant here is the moment action on behalf of the force F, rotated clockwise. The same, the distributed load rotates clockwise around the point A. So the moment of the distributed force sign in the point relative to the point A is the same sign as of the force F, and of another sign than of the assigned moment. And we can find that here the magnitude of the bending moment is 27 kilonewton per meter. Considering together, we can use as well the formula we had from the previous one article, that the bending moment here equal to counting from the point C to point B and to point A consists of point the moment is applied in the point C, but the moment is free vector. It can be distributed to any other point. And point F by the leg A equal 2 meter minus distributed load in the numerator product by squared x is for the point A 4 meter divided 2. 4 meters is the distance between the point, distance of the action of the distributed load Q. So we can find that this all considered together is equivalent to minus 27 kilonewton by meter. And in the middle of this element AB of the mechanical system, we have 15 kilonewton by meter. Is just because what magnitude of what of x we have to assign to that. Yeah, and after the finding of magnitudes and the characteristic points, magnitudes of the bending moment and the action of the external load, and the characteristic point of CB element of the mechanical system, we have plus 7, minus 11, minus 11, and minus 15, minus 27 here. We must to adopt this bending moment diagram for use for the Vereshchagin approach, finding the product of the to find the product of the bending moment diagrams and action of the external load, and the second one diagram of the bending moment and the action of the unit force. So for the this is for the first segment, we have a shape of tie diagram of the bending moment like a twisted trapezoid. Perhaps we can substitute this diagram by two triangles, right angle triangle here. And this one triangle is on the leg 7, another one on the leg 11, and the common leg is the length of the length A of the segment of the element of mechanical system CB. So this is a substitute of twisted shape of diagram of the bending moment of the external load action on the element CB of the mechanical system. Or we can say frame. We substitute by two right angle triangles. This diagram 1 by 2. The diagram of the bending moment action on the element of mechanical system AB. We can substitute by one right angle triangle diagram is on the leg 11, and the H is 4 meter. Another one right angle, another one diagram with the base 27 and the H 4 meter, and we will have the trapezoid form of the trapezoid shape of this diagram of the bending moment action on the element AB of the length 4 meter here. But this will be trapezoid, but we have to account as well the parabolic segment of this diagram, subtracting it of the total of two triangular diagrams of the bending moment on the same leg AB. So to find this, this h of this parabolic segment, or we can use the known formula of determination of the h of the parabolic segment as QL squared, Q multiplied by L squared divided by h, it is 4 kilonewton by meter here. Yeah, and as we have the distributed load 2, and we have the length 4 meter. By the another way, we can use the known from the previous one, article 3.7, the mathematical equation of the bending moment in the AB element of the assigned mechanical system considered. And we can find the middle line of the trapezoid. The middle number of 27 plus 11 is 38 divided by 2 is 19. And if we have on one hand the magnitude of the moment equal to 15 kilonewton by meter, and on the other hand we know that the middle line of the trapezoid would be here 19, so difference equal to 4 is the h of this very small segment of the parabolic shape to the linear trapezoid consisting of two triangular shapes of the trapezoids. So and besides of the adaptation of the diagram of the bending moment on the assigned mechanical system and action of the external load, we as well have to have to find the displacement in the assigned directions, the direction horizontal displacement of the point C, vertical displacement of the point C, and the bending angle in the mechanical system of the point C. We have to have the bending moment diagrams under the action of the forces applied horizontal to the point C here, applied vertical to the point C, and the bending moment. The bending moment, if applied in any point, it diagram distributes to all points of the mechanical system. So this is easy because it's assigned the bending moment equal to 1. This one of 3 efforts in the directions of finding the displacements of the point C of the mechanical system. So we use this diagram as one magnitude and action of the unit moment. P3, this moment is not for this moment. P3 equal to 1. And this is a P2 unit force directed upward applied to the point C, and we have linearly inclined magnitude of the bending moment. The maximal we have in the point A, this equal to the product of unit force to arm. Arm is 4 meters, so the magnitude of this moment is 4. And we have to assume that we have to remember that we determine the bending moment diagram on the stretched fibers of the mechanical system. The same here. On the stretched fibers, we apply in the transverse direction horizontal, the unit force equal to 1, and the bending moment diagram on the BC element of the mechanical system will be inclined like of the triangle shape, and for the AB element of the mechanical system, it will be even distribution of the bending moment. This is the diagrams of the moments and action of the unit forces on the considered mechanical system. Okay, so having the diagram of the external load of the bending moment adjection of the external load applied to the assigned mechanical system, and having the diagrams of bending moments of elements of the mechanical system and action of unit forces in each three of the directions. We have to find the displacement which in. We can substitute the solve into the equation of the for the calculation in the equation of the determination of Mohr integral using the method of Vereshchagin. As in this case, we use already the denominator with characteristics of rigidity of the transverse sections of the elements of mechanical system. They are specified as equal for two elements of mechanical system, A, B, and BC. So we have AE, and we can derive this out of the brackets in all of the determination, all of the calculations. And in the brackets, by the elements of the mechanical system, for the first one, we consider the products of the area of the diagram of the bending moment and action of the external efforts by the ordinata of the diagram of the bending moment and action of the unit force. So as, for example, for the first one, AB element of the mechanical system, this one is a diagram of the triangle shape, triangle shape. The one is the base of triangle is 27, and the height of triangle is 4 meters. Is a big triangle with not with the area of the segment deducted in the next, subtracted in the next from the area of this diagram complex. So the half part of the area of the base of the triangle 27 is a magnitude of the bending moment, kilonewton by meter, multiplied by 4. 4 is the height of the triangle, the length AB, element of the mechanical system, and multiplied by 2. 2 is the ordinata of the action of the unit force in the horizontal direction applied to point C. This ordinata determined even distribution of the bending moment equal to in the leg in the element of mechanical system AB. So this 2 is the factor in the first sum and under the brackets. The second one is the area of second triangle in the decomposition of this one diagram of the bending moment and action of the external forces. So 11, we have the size of the base of triangle, the h is 4, the area is 11 multiplied by 4 and 1/2. So that is 11 multiplied by 4 and 1/2. And we multiplied by 2. 2 is the under the location of the center of area of second one triangle when we decompose this trapezoid diagram into the two triangles, and the one negative subtract is the parabolic segment of the diagram. For each segment of the decomposition of the original diagram, we have to have the location of the center of the area. For the second one, we have location here, 1/3 part from the point B to the left and 2/3 from the point A, as a property of the triangle, of the location of the center of the area. In definite one case, it's not so much important because it is it's not so much important the location of the center of the area of definite each one segment of the bending moment diagram, because the distribution of the bending moment and action of the unit force is even. So independently on the location of the point, the ordinate of the bending moment diagram and action of unit force of P1 is 2. So we multiply by 2 again, and we subtracted the area of the parabolic segment with a sign minus of the diagram. We decompose this one big diagram bending moment into 3 segments. One segment is one triangle with the base 11, another one triangle with base 27, and the segment of the parabolic diagram with the maximal height of 4. So area is of this segment of the parabolic diagram is 2/3 parts multiplied by 4. 4 is the height of the parabolic segment, and multiplied by 4. 4 is the length of the parabolic segment along the element of the mechanical system AB. And multiplied by 2, 2 is the magnitude of the bending moment of for element of the mechanical system AB on behalf of action of unit force applied in the point C in the horizontal direction here, element 2. And the second summand in the determination of Mohr integral, so mean finding the horizontal displacement of point C using the Vereshchagin rule by the product of the area of the diagram of the bending moments on the elements mechanical system product by the ordinata of the diagram bending moment and action of unit force in the definite one place of the location of the center of the area of the bending moment of the external load. So the second summand is the first is a factor derived from out of the brackets, and the second here we have the areas. We have 2 triangles of the shape of the diagram. One is the negative shape diagram is with the, excuse me, with the leg by 7, with the leg 7, with the leg 7, and the height of triangle is 2. 2 is the height of BC element of mechanical system, and we product this diagram area of triangle. We product on the ordinata with a very small ordinata located 1/3 part from the point C and 2/3 parts from the point B, and the ordinata here we have to find, and we product by this ordinata is 1/3 part, and the ordinata is 1/3 part multiplied by 2. 2 is the maximal magnitude of this triangular, of this bending moment diagram for this definite one element mechanical system with a maximal magnitude equal to. So here we have 2 multiplied by 1/3 part. Two multiplied by 3/4 part. Yes, and the second is by 1/3 part. 2 by multiplied by 1/3 part. And the second area of the next triangle on the right from here, from the element of the mechanical system is of the base 11, and H is 2 as well. Area is 11 product by 2 divided by 2, and product by the ordinata of the bending moment diagram for the action for this definite one element BC and the action of the unit load. This is diagram ordinata is 2/3 part product by 2. So this like here 2 product by location of the center C2 located 1/3 part from the point B, 2/3 part from the point C, and the total h is 2. So we can find the extent from here to the point C, and we can adopt the magnitude of this bending moment at the actual unit force if we have maximal 2, but for the 1/3 part from this point B to this definite one ordinate, we have 2 multiplied by 2/3. This is 2 multiplied by 2/3. This are. And after the fulfillment of the calculation, we have the displacement in the horizontal direction of the point C equal to the grade in the numerator. We have 140.67. In the denominator, the rigidity of the transverse section of the element mechanical system. The same we got using the direct determination of Mohr integral by using the mathematic formulas for the bending moments in the article 3.7. Yeah, so this is correct find. If we will adopt the rules of the dimensions of the international system of dimensions, so elasticity modulus will be megapascal, and the moment of the inertia of the area of the transverse section in the cubic meter, but meter in the power of 4. So in this case, the displacement will be in the meter, the final magnitude. Accordingly, we determine the vertical displacement of the point C under the action of the force of the external load in the point C. We applied vertical load equal to 1. We have now the bending moment diagram in the BC element of the mechanical system, and we have linearly implied magnitude of the bending moments on the stretched fibers of the AB element of the mechanical system. So we have to multiply the area of the segments of each of all 5 segments for the considered mechanical system bending moment diagram and action of the external forces. And on the diagram of the bending moment action of this unit force directed upward applied to the point C. In this case, if we will do that, we will know the displacement of the point C and the external load assigned for the considered mechanical system, displacement upward. To do that first, we can derive the common factor out of the brackets, and the brackets we have the for the AB leg, we have to find the areas of all the elements of the diagram of we adopted to use for Vereshchagin rule determination of Mohr integral. And we have to find the areas of 3 segments of segment of triangle shape with a base of 27. The h 4 meter is the length of AB element of the mechanical system, and the second area of the element triangular of the triangular segment of the bending moment diagram with base 11 and the h 4 meter as well. 4 meter here we can see on the assigned draft of the assigned mechanical system, and the area of the parabolic segment subtracted of the common total of the previous 2 areas. And each we have to multiply by the ordinate of diagram of the bending moment. We change the signs. Here we have minus sign, and here we have plus and plus, and here we have plus, and here we have minus sign. Why? This is due to because the sign rule, the diagram of determined on the stretched fibers of the AB element mechanical system, and the action of the force applied upward is of the another sign as a previously considered direction of determination of the diagram of the bending moment and action of the horizontal force in the applied to the of horizontal unit force applied to the point C. So we have to change the sign as these two diagrams of the bending moments when we determine the ordinates of the diagram of bending moment and action of unit force for considered options located with other signs here. And so we had minus, and therefore the first one, the ordinate is 2/3 part of 4. 4 is the maximal magnitude of the bending moment diagram and action of unit force applied to the point C upward. 2/3 part is the projection communication with location of C1. C1 is 1/3 from the point A and 2/3 from point B along the total length of the element mechanical system as we have 4. So we multiply 4 for 2/3 part to find this one magnitude of the bending moment and action of unit force. 2/3 product by 4. And for the second one, triangle in the decomposition of the bending moment diagram for AB element of mechanical system, we have that the its location on the AB element mechanical system is 2/3 part from the of 2/3 part of 4 from the point A and 1/3 of the point B. So we can find the magnitude here is 1/3 part of 4. So 1/4 part of 4, and we remember that we have another sign as in the previous one. Calculation due to the diagram, the bending moment and the unit forces have another sign than the diagram. Or in the previous one case is positive, this is negative. So we decompose in this manner. This is the area of the parabolic segment, and this is 2. 2 is the magnitude in the middle of this bending moment diagram and action of unit force as the center of the area of the subtracted parabolic segment is in the middle of the by the length of the mechanical system element AB. Yeah, and after the calculations, we have that the displacement in the second direction here, in the second direction of the point in the vertical direction. So first we found the horizontal displacement. The vertical displacement is minus 152 divided by the characteristic of rigidity of the transverse section of the elements mechanical system equal for both two elements AB and BC. And the angle of the section C torn or bending at the point C. So we can determine this by the same way as the previous one, translational displacements. This is angular displacement, but the same sequence of determination, only we use the ordinates of the bending moment diagram taken from the diagram here of the same sign as the previous one when we found the displacement in the upward direction of the point C, and the same here we have the same sign diagram, but this is evenly distributed diagram, very easy to use as the ordinates all of the diagram is 1. The bending moment is any moment, is the free vector, it can be applied to any point. To depend on the location of the point of the section for the determination of the bending moment diagram magnitude. So we have everywhere just only one factor of the ordinate of the bending moment diagram and the action of the unit bending moment applied to the point C. It gives the magnitude of this unit moment is 1, and it gives a bending moment diagram magnitude in any points equal to 1. So this is like the first one mathematical equation, but of the another sign is the bending moment diagram and the action of the unit moment is on the other side of the mechanical system. Here we had the positive, here we have negative signs of the bending moment diagram. In the first case, figure 3.8.3a, and the action of the unit force applied leftward to the point C, and in the figure, on the figure 3.8.3c, we had even distribution of the bending moment diagram and action of the unit moment applied to the point C counterclockwise. So the diagrams are of the other side, so we change the signs in the determination of Mohr integral using the Vereshchagin rule. And after calculation, we have that the angular displacement of the point C is minus 69.33 divided by the characteristics of the rigidity of transverse section of the elements of the mechanical system, elasticity modulus, and moment of the inertia of transverse section of elements of the mechanical system. Questions and comments. 3.8.1. The conditions under which it is possible to use Vereshchagin's rule to determine the Mohr integral by multiplying the diagrams of forces when finding the displacements of points of nodes or the nodes of a mechanical system. The conditions are that the one of diagram have to be linear. Usually this diagram of the bending moments of the mechanical system and the action of the unit effort could be unit force or unit moment in the required direction for determining the displacement, translational or angular displacement of a definite assigned section of the mechanical system. 3.8.2. Mathematical form of the product of diagrams of Mohr integral using the Vereshchagin rule and at the linearity of unit of force, the bending moment diagram. The mathematical form of determining the Mohr integral is that the integral of in the integrand of product of two diagrams of the bending moment equal to product of the area of one of diagrams by the magnitude of the bending moment of the another one diagram in the projection communication with the location of the point of the center of area of the first one diagram. That is the mathematical form of product of diagram in the Mohr integral using Vereshchagin rule. 3.8.3. Determine the diagram bending moment of the specified lowered bisections of the mechanical system. Sometimes if we have the curvilinear diagrams, we can simplify. It could be usually diagrams of the external load of bending moment and action of the external load, maybe distributed load. We can use the decomposition of this diagrams into the simple form, into the triangular form, or maybe into the trapezoid form, but usually in the triangular form. It can be for the trapezoid diagrams into two triangles, trapezoid shape of the diagram of the bending moment, we can transform to two triangular diagrams of bending moment instead of trapezoid, or for the non-linear trapezoid, we can as well count the parabolic or other shape of the segment to the trapezoid form. 3.9. H point for the determinant of bisections of mechanical system of bending moment diagrams under the unit efforts applied at the points and in directions of the displacement sought. Yeah, first we have to coincide the limits of determination of the integral Mohr with each one element of the mechanical system. And we have to do this consequently, usually starting from the point which displacement we look for, and gradually to the keep the sequence of determination of the integral of Mohr to the support of the mechanical system. 3.H.5, finding linear and angular displacement of specified point of the mechanical system using Mohr integral and Vereshchagin method to produce the diagram in the Mohr integral. Linear and angular displacement we can find by Mohr integral. Within Mohr integral, we in the numerator we have the integrand. The integrand is the grade. In the numerator and the grade, we have the product of the diagram. One diagram of the bending moment of the under the action of the external force. Another one diagram is a diagram of bending moment under action of the unit force in the unit force applied to the assigned point of determination of the displacement in the required direction. The force may be moment. To be honest, it's more correct to say the effort applied to the point in the direction which we have to find the displacement. And after that, we can use Vereshchagin rule if we do not have the mathematical equation. Mathematical equations of the diagrams of the bending moments, and we have only the magnitudes of the bending moment and the definite points. To use Vereshchagin method, we use first we find if one of the diagram, usually the diagram of the bending moment and action of unit forces, are of the linear shape. In this case, we can instead of finding the integral itself, direct finding of the integral, we can find the product of the area of the curvilinear, maybe parabolic linear area of diagram of any shape, maybe no linear shape, the area, and we have to find the location of the center point of the area of the curvilinear diagram of the external force, and in the projection connection to this location of this center of the area of the bending moment diagram at the action of the external force. For the same location point, we can find the magnitude of the bending moment accordance with the diagram of the moments and action of the unit force in the required direction, in which we have to find the displacement of the mechanical system. And this is substitute this product of the area of the diagram to the by the magnitude of another one diagram at the corresponding point of the location of the center of the area of the first one diagram. This is a substitute of the direct determination of Mohr integral by mathematical transform. Thank you.